Reviewing the scan data, we realize that the actual axle outlet and bearing seating area needs to be rebuilt in order to obtain maximum accuracy and also to have the correct relationships with all the other axles and gears that the specific axle interacts with. The idea here is to use material deposition or additive manufacturing to fill the entire axle seating and machine it back to its more precise definition. This will be done by creating surfaces for each feature in the axle seating area. So let's dig in and see what the reverse engineering application in NX has to offer. We start off by using the polygon modeling tool SNP to smartly divide the convergent body into two pieces. We select along the chamfered edge on the top and realize that we have to use a combination of selection rules such as tangent facets and rough brush, as there are some discrepancies in the convergent body. Discrepancies that we will fix by reverse engineering it. We use the rough brush to limit what's selected on the inside, and finally flood fill to select everything in between. Once happy with the selection, we hit OK to confirm and divide the convergent body accordingly. We check the result of the divide operation, hide the convergent body representing the interior piece that we will reverse engineer in just a short while. We fill the holes using the polygon modeling fill hole function on the remaining main convergent body that will remain as is. We reverse the hide status and bring back the inner portion of the axle outlet and seating area that will be reverse engineered a bit more precise. For smart selection and quick surface generation based on the convergent body, we will color code the convergent body. There are two really good options here, and the first one is detect primitives. That does just what the name says. The result is a color code on top of the convergent body that tells you what type of primitive surface is corresponded to each color on top of the convergent body. We specifically note red to be planar, blue to be cylindrical, and yellow to be conical surface types. All great help to continue defining the surfaces later on. In addition to the detect primitives, there is also facet body curvature. That is a great help to limit areas. Adjusting the threshold values allows you to primarily refine your color coding according to your specifications. Using the limits of the color-coded areas we have just created, we are now able to easily define surfaces based on type of surface and the limited color areas. As we are to create primitive surfaces, such as cylindrical and planar faces, we start by just showing the fit freeform and what it does, just to show it. We use a chamfer face to show what it does. The system does exactly what we tells it to and creates a fit freeform surface on top of the chamfer. But as we know that this is a chamfer, we undo the result as we do not want this. Note that I switch between the curvature detection color code and normal shading to review the surface result. Also note that you can switch back to the curvature color coding at any time. With the support of the color-coded scan data, we will now start to reverse engineer the actual analytic shapes of the scan data. We primarily start to create the outer cylindrical shape on the inside of the transmission housing by using Fit Surface and the option Fit Cylinder. By selecting the limited blue color code region representing the cylindrical shape, we rapidly create the cylindrical face corresponding to the selection. We review the result and note that it is slightly off. This is due to that the color-coded area from the facet body curvature color coding is a bit rough. We note areas where the blue color representing a cylinder is interfered with other colors that causes the result to be a bit off due to the selection. We could continue by trying to refine the threshold values for the facet body curvature color coding. However, this might be a bit timely and we choose an additional option to directly set the color coding so that we get the precise result that we are expecting. In addition to the detect primitive and facet body curvature, you can manually manipulate the color code to better fit your purpose. Simply set or inherit the color that you want to change to and start selecting areas that you want to recolor by setting the appropriate selection rule. As we only want to correct very small areas here, we leave it at single facet. Once the color coding have been fine-tuned, we now try the fit cylinder option again and find the result to be satisfying. As the just created cylindrical face is a bit small, we resize it by simply extending both ends using extend sheet. Here with the selection rule outer edge of face set to include all edges of the sheet body. We adjust so that the sheet slightly interfere with the convergent body that will remain as is, and so that the top end is slightly oversized as it will be trimmed back to its final position. As this is going to be a solid body that will be incorporated into the convergent body, we seal off the bottom of the cylinder by using bounded plane. In order to create and seal off the top of the cylinder, we turn to Fit Surface and the option Fit Plane. As the resulting surface is a bit too small, we extend it to be oversized and better fit our purpose. By changing the shade to normal part shading with edges, we can better see the result of our created surfaces. We can at any time set the display back to color coding to continue create quick fit surfaces where the emphasis is on color coding for clarity. As we want the result to be an enclosed volume and a solid body, we combine the surfaces by using trim and extend together with sew. The result will be a solid body that can be united with the base convergent body. We unhide the convergent base body and unite the two solids. Note that the just created traditional analytic solid cylinder will be united with the convergent base solid body. Also note the really cool thing that you can add a regular blend feature to the resulting edge, and the result is parametric. As you probably already are thinking, this enables process automation. We reverse the hide status and bring back the convergent body representing the hole for the axle. It's time to quickly reverse engineer the axle outlet and the bearing seating. We toggle the color coding on for the facet body curvature by setting the display to phase analyze, as this will help us create the various cylinders representing the axle outlet and the bearing seatings. With the color coding on, we can now create the various cylinders in one go by selecting the respective colored area representing each required cylinder. Note that by using closed as fit condition, the full cylinder will be created even though the selected area is only represented by a piece of a cylinder. We hide the reference color-coded convergent body and turn on regular shading to inspect the result of our created surfaces. As we're happy with the result, we move on to create the planar levels along the axle, providing limits to the bearing seating. We use the Fit Surface and Fit Plane option and select all the levels in one go to create the planar levels. The resulting surfaces are all extended to become oversized, and yes, you guessed it, they will be trimmed back to their final shape. As just stated, the oversized surfaces are all trimmed back and also joined in one go by using Trim and Extend and the option Make Corner. Ensure that the trimming directions is correct so that it correlates with your expected resulting shape. We unhide the reference convergent body and study the result. To ensure the coaxial accuracy, we use synchronous modeling and the coaxial requirement in order to guarantee optimal relationship between the interacting axles and gears in the transmission. Here we add the coaxial requirement to all the cylindrical shapes in order to be coaxial with the Y datum axis, as this is the reference used while scanning the physical part. As we did not really check if the synchronous modeling and the coaxial requirement was really necessary to add, we suppressed the associative coaxial requirement from the feature list and analyzed the status of the centers of the cylinders in relations to the absolute coordinate system, that is the correct reference here. We can see that it is slightly off, and we are now 100% sure that with the coaxial requirement active, all the cylindrical surfaces are coaxial to the reference axle, and we will obtain an optimal interaxle and gear relationship. Maybe even better than the original, as this failed alignment could be the reason for the damage in the first place. We check again with the coaxial requirement features active in the feature list, and we now see that the alignment issue is fixed and all the cylinders align perfectly. We move on to the details of the cylinders and the recess areas. With the initial detect primitives, we know that the blue areas in the recess areas of the cylinders in the faceted body curvature color coding are planar. We therefore once again turn to reverse engineering and fit surface with the fit plane option. When selecting the small planar recession color-coded area representing the top face of the recession, we realize that the selection becomes wrong. This is probably because the planar face is not properly limited by a different color. We therefore, in this case, manually recolor areas that is not quite correctly participating the color-coded boundary to the area to be planar. We quickly recolor the failing area by using Paint Facet Body and select the failing facets by using the selection rule Single Facet. We then give Fit Plane Surface another go. Note that you can create all the fit surfaces in one go. We review the result and note that the just created surfaces are a bit small and needs to be extended. This is easily done by using Extend Sheet. And also here you can select all the sheet bodies and extend in one go. For the final shape of the recession areas, we use Trim and Extend and the Trim Corner option for automatic joining. We repeat the same procedure on the other side. We bring back the cylindrical reverse engineered sheet body and incorporate the recess areas. We continue by adding the detailing features, such as blends, to the reverse engineered sheet body. It's time to unhide the convergent base body and incorporate the detailed and optimized reverse engineered axle outlet and bearing seating area. We do this by simply trimming the convergent base body with the just reverse engineered sheet body. We finalized the reverse engineering session here by adding some chamfers. Note that the regular chamfer feature are added to the trimmed edges of a faceted or a convergent body directly. How cool is that? Now with the damaged area fully reverse engineered and optimized, we wrap up this session. I hope that you all have enjoyed and got some great ideas and takeaway for your business. In other words, this concludes the reverse engineering and quick shape rebuild and optimization section. That is the third and final section in the series of total 3 tutorials handling reverse engineering on the NX platform. Myself, I'm now off to the shop floor to do some manufacturing and to get this engine started. This is Fredrik Sandblom for Siemens Industry Software, signing out.